Okay, easy ones to go over. You were supposed to do 4 of these without me. The last one I did was number 4, so I need the answer to number 5. So you didn't do this problem yesterday, even though I asked you the next 4 math workshop problems. Every group lose a point. Subtract the following numbers down to the nearest 10th place. Doesn't sound that complicated. 2 and 6 get a point. It was 5. Was that you as well?
Yeah, that was number 1.
No, it's not you. So 2 and 6 get a point. It is A. Okay, absolute value of -9 is B. Thank you. 6. No, it was Kaylee. Yeah, and no, I thought it was Sydney, but no, she Kaylee. 2 get a point. She already got it. 2 already got it. Okay, as for number 7, they asked for the median.
7.8.
7.8. Is it 8? It's D. It's B.
7 is D. The 2 groups that say
Hey, I said D.
No, you don't say
Everybody. No, he said 7.8. I said D.
I said D.
Okay. And the last one you were supposed to do without me was number 8. It says the mathematical average of the number of weeks in a year, seasons in a year, and the days in January. So this one is, for the most part, this one is probably the hardest of that set because you have to know some things. What did you say, Lloyd? D is incorrect. E is correct. Yes. 2 had it, and I'm mistaken, and then 3 I heard you. So 2 and 3 get a point. It's E. Okay. Let's go over this one. It's amazing how little I've heard from Kay before. There are 52 weeks in a year, 4 seasons, and there are 31 days in January. So to average, we need to add 52 plus 4 plus 31 and divide that by 3. And we should get to the 29. So 56 plus 31, which is 80 something. 5, 6, 7, 8, 87 divided by 3, which is how they got the 29. I'm not saying it was exactly 29, I'm just saying that's the closest. Okay, we're going to go over 9 and 10 tomorrow, and then 11 and 12 on Friday. One I'm talking over you is point. We're going to go over 9 and 10 tomorrow, and 11 and 12 on Friday. So if you were trying to get your group points, you would go ahead and have 9, 10, 11, 12 done. Okay, let's go back to what we were doing last week. I want to go far back. Well, not that far back. You did it on Monday too. You had to do a Fibonacci sequence and fractal spiral worksheet. I'm going to borrow Lloyd's for a second. It looked like this. Yours is now officially late. If you've not turned it in, yours is now officially late. You were reminded again and again and again. I wrote it on the board Monday and Tuesday. Surely you agree.
Does that count for me too?
Now you're still going to get most of your points, but at this moment it is now late. Where is it? You need to get this turned in. Moving on. Moving on. You already got it turned in? Yeah, I have a ton of okay. Most people have turned it in. Moving on, I want to talk about what you learned from that and how to use that for the rest of the year. So our plan for today. I want to show you some cool stuff involving Fibonacci. I want to show you a bonus thing that you can do to get you some extra points. And I want to do a lot. Let's talk about what you're going to do the rest of the week. So we're going to go over some stuff today. I'm going to let you finish 5.2, yada, yada, yay. Tomorrow we're going to do as many problems with 5.3 as we can, and we're calling it a day. We're not spending multiple days on 5.3. I don't like that activity that much. It's a good pattern, but it really ties better with the next chapter than this chapter. So this chapter is mostly with like patterns and sequences and series. Is there a pattern? Can you find it? Like with the Fibonacci pattern. On Friday, you will get to do a problem that's similar to the rabbit problem we're going to discuss today. It will be a group quiz. However, next week, when we call it quits on Chapter 5, it will not be a group test. You will be allowed, however, to use your textbook and any notes you've been taking in this section. So anything you write down I say today, your fractal spiral and Fibonacci worksheet, your 5.1 activity, anything you've been writing down, you will be able to use, but it will not be a group text. Okay, just FYI. The first thing I wanted to talk about was who this guy was. So I didn't pull that up. Let me Google that. I have this video I show near spring break. I have a video. Every great lose point. I have a video I showed near spring break, which does involve Fibonacci and its own Donald Duck, and you can have a point for remembering that. We're not watching that today. Okay, so there was this guy, and his name was Fibonacci, and they called him the greatest mathematician of the Middle Ages. And the reason they called him that is because, I don't know, he's crazy. So he's very smart. A lot of people get him confused with Leonardo da Vinci just because I don't know why. They just think they're Italian, I guess. But see, what happened to him is that he came up with a lot of stuff. So if we look, he has many contributions, which you've known about. You just didn't know they were due to him. He introduced the decimal number system. He came up with Roman numerals. He did math with Roman numerals. He defined the term algorithm, which is just how you work a problem. Good Lord. But the coolest thing I think he did involves the Fibonacci numbers. Okay, so did he invent this series? No. Me and Zach were discussing this. So did he invent it? No. He was the first to notice it and name it, and that's all that life requires. If you're the first one to notice a pattern and then name the pattern, you get the credit for the pattern, even if you didn't invent it. Yes, Jacob.
How did he invent Roman numerals?
Okay, so he changed the way they were using them. Well, let me rephrase that. He didn't invent them. He changed the way they were using them when they did math problems. Is that better? 2, you can have a point. Okay, but I don't even focus on the Roman numerals. I'm so fascinated with the Fibonacci sequence, I just can't even. So you know for sure that's going to make your next test. It is useful to know it is 1, 1, 2, 3, 5, 8, 13, etc. But as long as you understand you add the 2 previous, you'll always be able to figure it out. Okay, so I was going to show you a couple cool things involving the Fibonacci sequence because Zach and I were discussing it comes up a lot in nature. So, for instance, some claim that it is involved in patterns in the galaxy. And, of course, it's found in, like, patterns and things we see in nature, such as, see the spiral inside the sunflower? No. And this is the spiral you were supposed to come up with on the back of your worksheet.
I don't really see the spiral.
Do you see? You don't see the spiral?
I mean, like I said,
you do it in the.
But I don't see like.
But you do in the universe, right?
Yeah, I see
okay.
the universe.
Well, they claim it's in this. I get the flower. Yes, dear. Okay, so they claim you can see the Fibonacci spiral, which we got from the Fibonacci sequence in nature. They also claim that Fibonacci happens. The numbers within the Fibonacci sequence happen a lot in nature. So, for instance, if you have this certain kind of broccoli. They see spirals in it, yes. But also, if you count the number of points, or back to the flower, if you count the number of petals, more than likely the number you count is one of the Fibonacci numbers. That's why 4-leaf clovers are so rare, because 4 is not a Fibonacci number. 1, 1, 2, 3, 5, you didn't hear me say 4, so that's why 4-leaf clovers are so rare. Okay, so, and then pineapples, if you cut them, you can see a certain way, you can see the spiral within them, but also if you count the little peg things, or whatever they're called, I'm sorry, I'm not fluid in my food connoisseur or whatever. That is also going to be a Fibonacci number. The artichoke, if you cut it a certain way, it's going to have the spiral. A type of vegetable. And cauliflower, another type of vegetable.
Well, I know cauliflower, man.
It's also going to be.
Artichoke comes from the ground.
Okay, so even cabbage. So I have noticed it with the others I didn't notice, but cabbage I've seen before where when you cut it in half, I've seen the fractal
I
spiral.
thought that was on onions.
Onions as well. So you're going to see the fractal spiral a lot. Okay, I don't really get into that's a little above our league.
Like the red cabbage. I always thought that was.
Okay, so even our brain has some folds in it that kind of look like fractal dimensions, which they can tie back to fractal spirals. Okay, so, and they saw fractals in their school, in seashells, leaves, trees. You can see fractal spirals lots of places. Okay, while fractal spirals are super cool,
Hey, that's fine.
and obviously a hurricane looks like a fractal spiral, while fractal spirals are super cool, and can even be found in your body and nature, blah, blah, blah. It's found everywhere. What I'm more impressed with is how often it comes up, like I said, when you count things. So, one thing you could count are petals. So, on this flower, there's one petal. Every group loses a point. This flower has 3. And then the sunflower has 13. So one example of a Fibonacci number in nature is dealing with flower petals.
Hey.
Ryan, turn it off. I don't know who turned it on, but I'm hot.
I'm pretty warm in here too.
If you take your hands, let's be more specific. 2, 5, 6, and 3, you can have your point back. If you look at your hands, which you have 2 hands, that's going to be a Fibonacci number. You have 5 fingers, another Fibonacci number. You have 2 or 3 parts separated by 1 or 2 knuckles, still talking Fibonacci numbers. So even your hands are Fibonacci numbers. And last but not least, if you cut open, their examples are red pepper, lemon, apple. Really, seriously, anything. If you cut it open and count how many chambers, like, pepper has lots of different sections, how many seeds, stuff like that is going to be Fibonacci numbers. So, when you walk through the room, you pick this handout up. At the very bottom of this handout, it says Fibonacci Project. It is not mandatory. It is strictly bonus. We're going to say it's 5 points per example. I don't care if you steal some of the exact examples I just went over. As long as
include photos or graphics.
It says photos or graphics, so if you draw me a drawing, that's sufficient. 3, you have a point for reading. Most importantly, though, so let's say Matthew steals the 4 examples I just went over, so he's getting 5 points per example. He still has to write a paragraph. This is not elementary school. Your paragraph needs to have more than 3 sentences, so Matthew still has to explain it. But if he can pretty much say what I just said in his paragraph, he's getting 5 points per. Yes, dear.
So I can go and I can find those and take pictures of them and
Yes.
write like 3
I
paragraphs.
found 7 I found 8 sections inside my red pepper. I counted 30s, whatever the number is.
Is there a limit?
31 seeds. No limits. So you get lazy. Okay, so that's a good bonus opportunity, especially for those of us who, let's be honest, haven't actually done the 5.1 activity or the 5.2 activity on our own, and the chapter 5 test is solo, so we're needing a little help. Okay, at the top of that page, it says Fibonacci rabbits. So I'm going to show you a cute little video involving the Fibonacci rabbits. Now, this is supposedly, again, this guy was around way before me, so I don't know that this is legit. But why he discovered the Fibonacci sequence, or, why he noticed this pattern, supposedly has to do with this problem. I don't know that I believe that, but it is a problem asked nonetheless. So, I'm going to show you this video on the Fibonacci rabbits. Your quiz on Friday is not Fibonacci rabbits, but it is something similar. So if you understand how the rabbits work, you'll understand how the quiz on Friday will work. I know. Okay, let's see.
I still can't hear.
I know.
Solution to Fibonacci's rabbit problem. Hey man, fan.
Okay, get it together. Jesus, take the wheel.
It's Jason Marshall here with a special look at the solution to Fibonacci's rabbit problem from Math Dude episode 16. Here's Fibonacci's question. If two newborn rabbits are placed in a pen, how many rabbits will the pen contain after 1 year? To answer his question, Fibonacci wanted us to assume that rabbits always produce one male and one female offspring, that they can reproduce once per month, that they can start to reproduce when they are 1 month old, and that rabbits never die. So that
We get that this problem is ridiculous, right? Because how are you going to guarantee they always have a male and a female, they always reproduce every month, and that they never die? That's ridiculous.
What's the question? What's the solution? Well, let's think in terms of how many pairs of rabbits are in the pen at the beginning of each month, starting with the one newborn pair in the pen at the beginning of the first month. These newborns are too young to reproduce, so we begin the second month with one pair as well. It's the same pair, but they're now adults that are mature enough to mate. As a result, one new pair of rabbits is born at the end of the second month. So at the beginning of the third month, we have a total of 2 pairs. The original pair again mates at the beginning of that month, but the newborn pair does not. The original pair produces another pair of offspring. So at the beginning of the 4th month, we have a total of 3 pairs of rabbits. The original pair, their newest offspring, and their first pair of offspring, which are now adults. 2 pairs can now mate, and they each produce yet another new pair, giving a total of 5 pairs at the beginning of the 5th month. Now, 3 pairs can mate, so after the 3 new pairs of offspring are born, our total moves to 8 pairs. At this point, the sequence is 1, 1, 2, 3, 5, 8. What's the pattern? The trick is that each number in the Fibonacci sequence is obtained by adding together the previous 2. 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and 3 plus 5 equals 8. You can keep going and going on like this to find subsequent numbers, and after 12 months, you'll get 144 pairs of rabbits. In other words, the 12th Fibonacci number is 144. But is that how many pairs the rabbit pen would actually contain after 1 year? No. That's the number of pairs in the pen at the beginning of the 12th month, not the end. So we actually need the number of pairs at the beginning of the 13th month, which is 233 pairs, or 466 rabbits. But how does that compare to the exponential growth of the model where rabbit populations grow like a geometric sequence? The difference is huge. If the rabbit population grew like a geometric sequence and doubled every month, at the end of a year, there'd be 8,192 rabbits. And that's the story of Fibonacci and his rabbits. Until next time, this is Jason Marshall with this week's Math Dude Video Extra. Thanks for...
Okay, so I'm going to post that exact video again. Let's talk about this.
It's assuming that the rabbits will die, but they actually do die.
Okay, let's go back to this. It's always adding the 2 previous. Yes, that's how I figured out it was the 1, 1, 2, 3, 5. Notice how, my suggestions to you again for a quiz that's coming on Friday, notice how they draw the giant rabbits for the grown-up rabbits, the tiny rabbits for the baby rabbits. They do something to distinguish, hey, this one's a small one, this one's a big one, so you know which ones can or cannot reproduce. Notice how they make a drawing. If you think, while it is always adding the 2 previous, if you think I'm going to start with 1, 1, 2, 3, 5 and use the exact Fibonacci sequence on Friday, you are wrong. It is always the 2 previous, but you have to figure it out at the beginning. It does not start off with 1, 2, 3, 5. Surely we can find other sequences that can go by this pattern. This pattern is special, the 1, 1, 2, 3, 5 specifically with adding 2 previous. because it's the one that happens the most in nature. That's why it gets his name. That's why we need to know it. Okay, let's go back to Fibonacci. So another thing with Fibonacci, I don't know if you drew your fractal spiral correctly. So if you did not end up getting something like this at the end. So if you've messed up your fractal spiral and you want to see me, one lose another point. If you want to see me so you can fix it, I totally understand. Okay, I want to go over, and you need to get your textbook. I want to go over the answers to 5.1 because some people got a little confused. Where's your book? Get your book. You got like a minute before I go around. Get your book.
I got my book.
5.1. I want to go over the answers.
We're going back in time.
Yes.
No, you're not.
No. It's a group quiz and you won't.
I will not let you fail.
Okay. Last week we did 5.1 and some of us have the wrong answers. We understand what's going on. For instance, I know Hunter has like 7 or something wrong with. I know he understands the concept. I don't know. I know he has a number wrong. And he understood the concept, but he wrote down the wrong thing. So let's go over these answers really fast, just to make sure we're on the same page, because again, Chapter 5 test is going to be on your own, but you do have your book. So wouldn't it be great if your book had the correct answers? Okay, so let's look at 5.1, number 1. Okay, 5.1, number 1. Most people have the correct answer of, what is the correct answer? Yes. Yes, we can have a point. There is one pattern, but that one pattern involves 0 traps and all 7 triangles. Okay, number 2. What is the answer to number 2?
1.
3 said it first. He was quiet, but he said it first. There are 0. Okay. And this is how you could draw it. If you want to draw it out, you can. You don't have to. This is how a girl in 6th grade does it, and I think it's genius. A trapezoid needs 2 roofs. A trapezoid needs 2 roofs. So 2, 4, 6. We know there are 7 houses. We have to put a triangle in that last one. We have to put a triangle in that last one. So there's no way to not use a triangle. Literally impossible. Okay, number 3. What's the answer on number 3?
7.
So this is the problem that most groups have wrong. This is the one, Hunter. This is the one. So Hunter has 7. And I heard some of the other numbers. 1 is one of the other numbers. 5 get a point. Okay, so there are options. So the only possible numbers of dotted triangle rows are odd numbers. 1, 3, 5, and 7. So I can have this option where I have just the one triangle. I can have 2 traps, and then 1, 2, 3 triangles. Sorry, that was ugly. And then I could have 1 trap, and then all the rest would have to be triangles. So 1, 2, 3, 4, 5, 6, 7. Or I could do all 7 triangles. And the textbook eventually gets tired of drawing things, so they start using like T for triangle and P for trap. So you don't have to actually draw your little ugly picture, just in case you want suggestions for life. Okay, so the answer is, even though they're making the 8 different rooming patterns, It's not possible to have 2, you can't have 4, you can't have 6, so the only options are all odd numbers, 1, 3, 5, 7. So yes, Hunter had 7, but he also needs the 1, 3, 5. It's all the odds. Okay, number 4, what are the possible number of striped trapezoidal roofs? Well, my gut would say, how many can you have? You could have 3. If you had 3 of them, that would mean you have 3 traps and 1 triangle. So 1, 2, 3, 4, 5, 6, 7. True. You can have 3 of them. You can also have 2 of them. 2 get a point. You can have 2 of them. So 1, 2, 3, 4, 5, 6, 7. You can have 1 of them. So 1 trapezoid. 1, 2, 3, 4, 5, 6, 7. Or you can have 0 trapezoids, which means I have all triangles. Now, if you're like Miss Compton, you're drawing the same exact pictures. Notice that I've drawn the 3 traps with 1 triangle, the 3 traps with 1 triangle. I keep drawing the same pictures. The same pictures are answering the same question. It's just in number 2 they focused on the triangles. On number 3 they focused on the triangles. Number 4 they focused on the trapezoids. So really, once you figure it out, why does it matter which one they ask about? It should be easy. Okay, number 5. It says, yes, 3. There are 6 total. There are 6 different roofing patterns. You did say it very quietly. And if you need to list it out, you can always just start off with all triangles, 2, 3, 4, 5, 6, 7. And then you're like, okay, what if I add in 1 trapezoid? 1, 2, 3, 4, 5, 6, 7. What if I add in 2 trapezoids? 1, 2, 3, 4, 5, 6, 7. What if I add in 3 trapezoids? 1, 2, 3, 4, 5, 6, 7. Oh, but whoa, I'm only getting 4. Where are the other 2 coming from? Okay, so Miss Compton 2 gets 2 points because they can read today. The problem didn't say how many patterns do I have using all traps and all triangles. It said specifically I'm using 1 trap. So I could put that 1 trap in the front, triangle out the rest. 1, 2, 3, 4, 5, 6, 7. I could put that 1 trap after a triangle. 1, 2, 3, 4, 5, 6, 7. I could put that 1 trap in here. 1, 2, 3, 4, 5, 6, 7, and so forth. So I can keep on moving that 1 trap until I have him at the very end. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. In fact, most people had drawn this one in their textbook. I know Hunter and I had, because we discussed it could be the trap is in the front spot, trap in the second spot, trap in the 3rd, 4th, 5th, 6th, and that's how we came up with 6. So if you did it like that, that's perfectly acceptable. But yes, Jacob's right, that's how we came up with the 6. We start with it in the front and move it all the way to the back. Okay, that was number 5. Number 6.
8.
There are 4 different arrangements of roofs. Want to get your point? Yes. Okay, exactly 3 traps. So the question is, really, so Jacob said on the last one, why don't we start with the trap in the front and move it to the back? On this one, why don't we start with the triangle in the front and move it to the back? So it's triangle and then the 3 traps. So that was 1. But 2 is going to be if we move the triangle here. 3 if we move the triangle here. And then 4 if we put the triangle on the end. So if you want to draw it out, so trap, triangle, trap, trap. My traps are becoming more and more square. Trap, trap, triangle, trap.
I don't get that.
Or triangle, trap, 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 triangle.
You know what I'm saying?
Yes.
I don't get none of that. Like, how you know when to use the triangles or the trap?
Because in the problem it said to use 3 stripe traps, so that's why I used 1, 2, 3 of these. So I knew I had to have 1 triangle.
Oh, so you have to have 3 on these.
It had to have 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. And that's why I was just thinking through where to put the triangle.
Okay, I got it.
6, you can have a point. That was a good question. Yeah. And here's why we're going over the answers to this. Because, my God, I get tired of people asking me the same stuff over and over again. 7 says, what would be all the options if we only had 1 triangle? Well, Dumbo, which includes myself, because at first I had to think this through. Well, Dumbo, did you look at number 6? Because number 6 had exactly 1 triangle each time. 1 triangle, 1 triangle, 1 triangle, 1 triangle. So it is also 4. So on 6 and 7, if you don't have the same answer, you don't understand. Okay, as for number 8. As for number 8, asking for the number of roofing patterns, exactly 5 times the roofs. It's the same as 5. So 6 and 7 matched. And then 5 is supposed to go with 8. So 5, we got 6. So number 8, we should also get 6. Asking for exactly... number 5 asks for 1 trap on the nose. Number 8 asks for exactly 5 triangles. Anytime we use 5 triangles, we're using exactly 1 trap. It's always 1 trap, 5 triangles. Every single time. There's no other way to get to 7. The trap really covers 2 houses. Which is why someone in, well, I feel like I'm skipping ahead. Never mind. Okay, number 9. What is the answer to number 9?
There is no relationship.
Well, that's not true. Thank you, Jacob, for humoring me. You can have your point. I already drew stars, bomb, and everything. My gosh. Okay, number 10. It says, it follows from question 9 that we can, how can you use the observation from question 9 to find the number of room patterns when there are 7 houses? Well, it follows from question 9. To me, I answered 10 the same way I answered 11, which may be redundant, but it's what I did. So you can have 0 traps and 7 triangles. You can have 1 trap, but if you have 1 trap, you're going to have 5 triangles, because they have to add the 7, and a trapezoid takes up 2 houses. So that's 5 plus 2, which is how I'm getting 7. If I have 2 traps, I'm really taking up 4 houses, because 2 houses per trap. So I have 3 triangles. If I have 3 traps, I'm taking up 6 houses, so I've got 1 house left, so 1 triangle. And there's always that relationship. So how could this observation question 9 find the number of roofing patterns when there are 7 houses? We just need to know how many traps you want or how many triangles you want, and we can pretty much fill in the rest from there as to how many options there are, because we already figured out the number of options in 5, 6, 7, and 8. Okay, I feel like number 11 is the same thing, so I just drew an arrow. Number 12 is finally where we get to the big boy. If you know the answer to 12, I'll give you 2 points. It was what?
Number 12? 10.
Yeah, 10, 14.
Now,
11. 13.
Okay, so
21.
let's go through it. If we have 7 triangles, no trapezoids, how many options do we have? 1. We only have the 1 option. Okay, if we have Jacob, no. Hunter already said the number, I just can't acknowledge it. If we have 1 trap and 5 triangles, what problem was that? 1 trap, 5 triangles. No, it was number 3. Oh, number 6, it was 4. If we had 2 traps and 3 triangles, didn't we handle that? It is 6. I don't know why I wrote 4. It's 1, 6, and then is there 7? 2 traps and 3 triangles. How many options for that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I get 10. No. So you did need my help for that one, and then the last one is another 4. So it should add up to 21. Should.
did I not say that?
What? You did. Yeah.
How many points do I get?
You were getting it 1, and then you did some weirdo selfies, so never mind.
Did not try to get service.
Yeah.
How y'all get that?
Okay, so we figured out the 1 from problem number 1. We figured out the 6 from problem number 5, from number 8, or from number 5, either one. We figured out the 10, actually, you had to figure that one out with 11, which I did a terrible job of doing. And we figured out the 4 on number 6 or 8.
Did we get 2 points for that?
No.
What? Why not?
If you had till number 12 done, then I'm happy. I'm happy. I'm not mad at you after that. I do want to mention for you, because I know it's getting closer. I do want to mention, are there any questions about 5.1 besides Tyler's mad at the 10, which I'm going to show in a second? I do want to talk about that now. Look at your 5.2. Yeah. Look at your 5.2. Always add the 2 previous. Add the 2 previous. Lord Jesus. Yeah, it makes sense. Do you remember when we used to do 4 exclamation point and we discussed that was 4 times 3 times 2 times 1? Didn't someone joke that it should be 4 question mark if we want to do 4 plus 3 plus 2 plus 1? I don't know. Seriously, just add up the previous. So, I don't know. So there's no button on your calculator. Sadly enough, you got to take the time to do it. But you seriously just add up the previous. There is a formula for it. Did he show it to you yesterday? N plus 1 divided by 2? Okay, well those are my 2 pence. Okay. I think we'll change our whole planning life. I'll say we'll do, yeah, really. We'll say you'll do 5.2 tomorrow. Those who can finish 5.2 and do part of 5.3 will get bonus. If you get to 5.3. Yeah, however many you do on 5.3 is bonus. So if you do 5, it's 5 points.